One sec. All right, and we are live. Welcome back, everyone, to another Quantum Matter seminar. Today, we have the pleasure of having Michael Sentef from Bremen, who's virtually here sharing his slides, and he's going to tell us about his work on quantum control. And as usual, feel free to raise your hand or interrupt with questions at any time during the talk, or you can leave the questions for the end, either way. Please, Michael, take it away.
Yeah, thanks a lot, Adrian, for the kind intro and for the invitation to give this talk. And also great to see some familiar faces. I will talk about light matter control of quantum materials. And this, I realized this is a quantum matter seminar. So I will give you an sort of a hybrid perspective on quantum materials. And I will talk about Floquet engineering, which is you engineer a state of matter by periodic driving. And I will also, if time permits, briefly talk about cavities and how we can use the embedding of quantum materials in cavity QED type of environments to achieve similar effects as with Floquet, hopefully with some more flexibility and also with some more efficiency. And I would like to highlight would like to mention also that I recently moved to University of Bremen. This is the new website that you see down here. I'm also still affiliated with the Max Planck Institute in Hamburg, my previous affiliation. And we're always looking for good people to join our lab. Okay, so that's the introduction. So when we think about light matter interactions and non-equilibrium science, one interesting, one general phenomenon is actually life on Earth that is related to both of these topics. So Schrödinger already talked about life and the key importance of non-equilibrium for life, of course, because as you know, life has to do with the fact that we're not maximizing our entropy, but we're actually getting rid of entropy to the universe, and we take in high energy food or low entropy food and dump the entropy back to the universe. And the thing that keeps us running as a motor is, of course, the sun. And at the same time, light matter interactions are also very important for life on Earth because, for example, it controls via photosynthesis the creation of this low entropy food that we're taking in. And also more broadly for the stability of matter, because the stability of atoms, for example, is dictated by the strength of the Coulomb interaction, which at the end of the day is mediated by the exchange of photons. So the strength of light matter interactions also plays a key role here. So it's very good that we have this kind of system going, and I would like to convince you that non-equilibrium and light matter interactions are not only relevant for biological processes and for us to even have come into existence, but also in materials. And the overarching question that I would like to ask is, can we employ light matter interactions to change materials' properties? Now, if you look up the strength of light matter interaction in nature, it's given by the fine structure constant. And it has two properties that seem to be detrimental to our goal. It's a constant, and being a constant seems to contradict the paradigm of change. And also it's very small. Its value is in dimensionless units is 1/137. So it's a pretty small number, which is good because it makes quantum electrodynamics controlled theory. But at the same time, of course, if something is small and we want to have big changes, again, this seems to not be the ideal setting. However, we know that we can use I'd like to think about the control of materials with light on this two-axis schematic diagram here. So there are two ways of getting around these obstacles. One is to drive a material with many, many photons. For this, we have lasers. Many photons that interact weakly with our matter can still, of course, induce big changes. But on the other hand, we can also think about the strength of coupling as being tunable. And the way to go here are, in fact, cavities. So on the one axis here, we have strong laser driving. This brings me to the regime of non-thermal quantum materials and Floquet engineering, which I will explain in a minute. And on the other hand, we can also confine light into effective smaller volume and thereby enhance the density of states of the modes that we're interested in, that we would like to couple our matter excitation to, and make them more strongly coupled effectively at the expense of reducing the density of states of other modes that anyway we don't care about. So this is somehow the general scheme here. And in my talk, I would like to convince you that either of these two cases are relevant and interesting, and B, that there is even a connection. And I think thinking a bit ahead into the future, I think we've already gained some knowledge about non-thermal quantum materials, driven quantum materials, and Floquet. We're beginning to gain some knowledge from the theory side on cavity quantum materials. Also, some experimental results are coming in. The most interesting regime will be the intermediate regime. There's plenty of space in between these two limits. And I think this will be, in the long run, the most interesting to explore. And just as a shameless plug, we've written 2 review articles, one of which was co-authored by yours, Alberto, in Reviews of Modern Physics, if you're interested in getting an overview of what has happened in the past 10 or 20 years in this field of non-thermal quantum materials. And more recently, we also reviewed cavity quantum materials, which is a more emergent field with, at this stage, probably 90% theory papers and about 10% experimental papers. So these are the limiting cases of this talk. Okay, so now I've sort of set the stage. Let me give you one example. So the example that I'm choosing is, can one engineer the Haldane model dynamically? So what's the Haldane model? The Haldane model is a model that Haldane wrote down years before graphene was even synthesized. He wrote down a model that is basically graphene decorated with an AB sublattice potential and a complex second neighbor hopping, e to the I phi times T2. So an electron that hops along a path, let's say from A to this B side to the other side and back, will pick up a phase e to the I phi in its wave function. And this corresponds to a local flux, or if you like, a staggered magnetic field. And these are fictitious fields. So he just invented a Hamiltonian that had these fields. We don't know how to create them. The interesting consequence that he derived was that this gives rise to a quantum Hall effect without a macroscopic magnetic field. So this he showed in this seminal paper, for which, among other things, he got the Nobel Prize in 2016. So the phase diagram of this model looks like this. So you have graphene at the center, where you don't break time reversal, you don't have this complex second neighbor hopping, and you don't break inversion symmetry by an AB sublattice potential, then you have gapless graphene. And if you break time reversal more strongly than inversion, then you end up in this quantum Hall state, the yellow lobes here. And if you break inversion more strongly, then you're in a trivial insulator. So that's the idea. And so this would be an interesting topological state of matter, in fact, a Chern insulator. But of course, in reality, we don't have this in graphene. So one idea of in fact generating the state was then proposed some 2 decades later, namely to use graphene and break time reversal not by a staggered magnetic field on the atomic scale, but instead to use circularly polarized light to induce the same effect that this complex second neighbor hopping has. Okay, so circularly polarized light clearly checks one of the requirements. It does break time reversal, right? It has a handedness, it has a well-defined direction. It gives you a well-defined direction in time. If you reverse time, you turn right-handed light into left-handed light and vice versa. So that's good. But how can we actually see that this gives rise to this Haldane model effectively? And for this, we need the concept of Floquet engineering, which I mentioned before. So let me give you first a classical example of Floquet engineering to get some intuition. And this is the so-called Kapitsa pendulum, which is essentially a way of stabilizing a metastable state and changing an effective potential energy landscape, an effective Hamiltonian that a material has. So right in the Haldane model, we would like to generate additional terms in the Hamiltonian that are not there in equilibrium. So the Kapitsa pendulum is a classical example. So you have a normal pendulum, but you start shaking the suspension point of the pendulum. I guess some of you have seen this before. And this inverts the effective potential of the pendulum. So the normal pendulum will oscillate about its usual equilibrium point, and the driven pendulum will oscillate about this new inverted stable point. So it has turned the metastable point in the upward position into a new stable minimum, and the driving on top also destabilizes the original vacuum state of this pendulum. So this is a classical example. This you can do in the with first-year students once they know how to solve differential equations. So now let's look at the theory behind this. So Floquet theory, what is it actually? It is a theory that maps the time periodic problem, a Hamiltonian. So given the time-dependent Schrödinger equation and the condition that the Hamiltonian is allowed to be time periodic, but with a period big T, which is related to a frequency. And essentially you do a Fourier ansatz. So you expand this in plane waves with some coefficients that are unknown from the outset, phi m, times a prefactor, which is similar to the e to the I kx for real space plane waves. But now you do this e to the minus I epsilon t. So you see that the time evolution is given by an effective or quasi-energy epsilon here. And this will turn into the eigenvalue, the Floquet eigenvalue of a Floquet matrix. And the time-dependent Hamiltonian under this ansatz is mapped to a quasi-static eigenvalue Hamiltonian, or a quasi-static eigenvalue problem with this Hamiltonian HMN, which is a big matrix. So it's the size of the original Hilbert space times infinity, times integer infinity. So you pay some price, of course, so you make the problem more complicated in a sense, but at the same time, you get rid of the time dependence, right? And the matrix elements of this Hamiltonian are given by the harmonics of the time-dependent Hamiltonian, just like the harmonics were used for the wave function as well, plus a term which is essentially a delta function in this Floquet index Mn times the frequency. So this is a shift of frequency. I'll illustrate this on the example of the Dirac cone of graphene in a minute. And this comes from the IDT term, from the derivative term in the Schrödinger equation. If you like, you can think of this as the absorption of M photons. This gives rise to shake-off states where the original energies are shifted by plus and minus integers of the integer multiples of the photon frequency. Okay, so this is nice. So what does it look like? So this is what Oka and Aoki wrote down. So they wrote down a Dirac fermion theory, just a linear band dispersion for the Dirac cone, coupled this to an AC field, in this case by minimal coupling. A of t is a vector potential of an electromagnetic field. Circularly polarized means that you have a phase shift between the x and y components. And if you insert this into the time-dependent Schrödinger equation for this 2x2 problem at each momentum point, then by Floquet theory, we map this onto a matrix, as I promised, which is now time-independent. And I'm truncating the matrix here at these Floquet indices plus and minus 1, just for display and because there's anyway an energy offset. So if the frequency is big, then these diagonal terms will grow in size up here, or or grow in negative size down here, and therefore they will become less and less relevant for the low energy physics that we're anyway interested in. So here in the middle, you have the original 2x2 block of the linear Dirac cone, and then you have these plus and minus photon frequency shifted blocks, and the off-diagonal terms, the coupling terms, they are essentially coming from the harmonics of the field term here, and sort of they conspire. So where these A's appear on the off-diagonals, that corresponds to it's a conspiracy between the circle, the handedness of light, and the handedness of the Dirac fermions. This you can just see by plugging this in and evaluating this expression here. So for example, for linearly polarized light, you would have an A here everywhere. For circularly polarized light, some of these terms cancel. And the important thing is that the subblock here, this has the A on the upper right, and the other subblock down here has the A on the lower left, and they don't commute with one another. And this is the signature of time reversal symmetry breaking. So what does the band structure corresponding to the 6x6 matrix, which you can diagonalize easily, then look like? It's the following. So for the central block, you just get the original Dirac fermion. Then you get the one shifted up by a photon energy, the one shifted down by a photon energy. And the hybridization terms give rise to two effects. So the one effect is that if you just think about this, you have a band, whenever you have a band crossing between the yellow band and the red band, for example, you open a gap when they hybridize via the vector potential. And this gives rise to the gap opening here. This is linear in the vector potential. It's linear in the field strength. And what's more important, and you also have the higher order gap openings when a band crosses with, for example, a higher order crossing. So let's say the +1 photon band crosses the -1 photon band, and so on. And they're smaller in size because they don't directly hybridize, but they hybridize indirectly. And what's more important for the purpose of emulating the Haldane model is that you want to open a gap at the center. And this is a second order effect. And it comes about from the fact that you essentially absorb a photon. So you go up, so you do perturbation theory, you go up from yellow to red by absorbing a photon, and you come back down by emitting the photon. So this is a process of order A² over omega. So it's, you need 1A to get to the intermediate state. You pay a price of the order omega, which is the energy denominator, and you come back down by another photon. So you have A² divided by omega. And as I mentioned, these green and purple matrices here do not commute with one another. So therefore, the process of first going up and then coming back down, or first going down and coming back up, these paths do not commute. So they give an energy difference, and this energy difference is the gap that you see here. And the gap is of the order A² over omega. So that's the physics behind the gap opening at the original Dirac cone. And of course, clearly, this is a manifestation of time reversal breaking. The fact that whether you first absorb and then emit, or first emit and then absorb, it does the order of things in time does play a role. Yeah, that's the whole point. And the sign of the mass term is determined by the chirality of light and also by the chirality of the Dirac fermions. And this is now an effective time-independent Hamiltonian. And this one can show in the high frequency limit that this really exactly emulates the Haldane model. And this is the finding of this paper 20 years after Haldane by Oka and Aoki. So this is all great. So I hope now you've sort of understood the essence of Floquet engineering on this quite simple example. So this sounds all very nice. And now the question is, of course, what can we do with it? Can we actually engineer materials at will? And does this bring us, does this open a completely new avenue here? And the answer is, well, not so easy. Actually, even though Oka and Aoki first wrote this down for graphene and had material in mind, the first ones to actually demonstrate the principle of Floquet engineering were people using waveguides in photonics. And Rechtsmann et al. Created this very nice example of a photonic Floquet topological insulator. where they have these chiral waveguides. And in the photonic band structure on this photonic honeycomb lattice, they created a band gap. In fact, not by breaking time reversal, but using the Z direction that goes into the board here, or into the plane, as a synthetic time dimension, if you like. So this corkscrew pattern of the waveguides breaks Z inversion symmetry and opens a band gap in the band structure of these waveguides on this honeycomb lattice. So that was their very ingenious emulation of the idea. And of course, this is sort of a bit simpler than in a material, because you don't actually have to apply a laser drive. The other thing, where the other platform where it was demonstrated was with cold atoms, because as usual, cold atoms have some advantages in tunability compared to solid state physics. And Jotzo et al. in the Tillmann-Esslinger lab in Zurich wrote this very nice paper in 2014 in Nature, where they took a honeycomb lattice with fermions and shook it in such a way that they also broke time reversal, sort of similar effect as the circularly polarized drive. And in this way, they could also show that there was a Hall effect like going on. And for a quite recent review by Mark Rutten and Nate Linden, I refer to this very nice paper here, where they review the state of the art of Floquet topology as of 2020. Great, but still no materials. So what went on? Give me another. Let me just interrupt here and give you another very nice example. So the inventor of Floquet topology, in my mind, Takashi, he's now working on Floquet engineering of living materials, which is another very nice example of Floquet engineering. Just to mention this very briefly, it's actually known that you can do Floquet optogenetics, or that you can do optogenetics, that you can actually address brain cells and make them sensitive to light stimulation. And then you can, it was shown that you can sort of steer the behavior of mice by coupling them to light, yeah? And now there's this idea of essentially in your brain, you have different signaling pathways. And if you can trigger them with light, in principle, you can also Floquet engineer these things. And I'd like to illustrate this with an analogy that Takashi brought up. Namely, think of a triangular relationship where you and some other person are interested in a girl. Of course, this could also be with other genders and so forth. So two people are interested in a third person, and they want to have a relationship with them. And now you want to competitively inhibit the signaling process of the other side. So what does this look like? How could somebody Floquet engineer his way to a relationship? Well, let's say the other person presents every 4 days a present to the girl. Let's say on day 2 and day 5. So this is a time periodic stimulation that hopefully favors them. From their point of view, but now how can you win? Yeah, so you're the other person. How can you win against this kind of Floquet engineering? And the idea is that, well, you just give her a present before he gives her a present. So you give her a present on day 1, he on day 2, and then you have the same periodicity, but you're earlier. And this is a way of Floquet engineering your way into a relationship here, I guess. That's the idea. And this looks a bit funny, but actually it's apparently it's related to this problem, and one can even write down a Floquet Hamiltonian according to Takashi for this process here on the left that kind of looks very similar to this problem here on the right. And this illustrates one important ingredient in Floquet engineering, namely if this present made her as much happier as this present, then in principle this wouldn't work. So if you can have the principle of superposition or linearity, Floquet engineering doesn't work. The time average would just be 0. But because it's nonlinear and your present, if you're first, makes her more happier than the second present, if you have kind of a saturation behavior, then Floquet engineering works. Yeah, this is like optical rectification, if you like. So if you have some nonlinear potential, you can optically rectify by periodic drive, and then you can actually induce an effect. So this illustrates the importance of nonlinearity in your Hamiltonian in order to be able to Floquet engineer an effective new potential that wasn't there before. Okay, with this intermezzo, let me just briefly mention that Floquet is now everywhere. Besides the examples that I mentioned before, it was already by Nate Lindner, Raphael, and Galitsky, suggested to be possible in semiconductor quantum worlds. Then we also have the example of time crystals, and even the idea of Floquet topological error correction. So it looks like everything's possible in Floquet world, but in reality, what about Floquet physics and materials? Now I'm finally coming to my point. So in materials, we predicted Floquet engineering in graphene, or the effects of Floquet engineering in graphene in photoemission spectroscopy back in 2015. And we even computed some pseudospin textures and predicted some higher order effects when there were additional level crossings. So this is going beyond the Haldane model. This is very nice. And in materials so far, one of the examples where it was actually observed was in the topological insulator Dirac fermion surface state on the surface of a 3D topological insulator. This is in the group of Nugetic at MIT, where they showed that one can have these side bands and potentially, I guess it's not in these plots here because here they use linearly polarized light, but you can clearly see that there are these side bands that I showed before in this center panel down here. And one has to say that to observe band structures in materials, of course, you have to do photoemission. In a driven experiment, you have to do time-resolved photoemission. And one of the big issues in the field, in fact, is that the dressing of initial states in the material or Floquet states looks very similar to the dressing of final states outside of the material. So if once the photoelectron has been emitted, it gives rise to the so-called Volkov states that can be photo-dressed. This is known as laser-assisted photoemission. It's kind of a competing process. And it's not so easy to distinguish whether the initial state has been dressed inside the material or the final state has been dressed outside of the material with the photon field. And that's one of the big issues in directly observing Floquet states in time-resolved photoemission. But okay, let's say in Nugetic's group, they did a thorough job in trying to distinguish these two effects and really showed that Floquet states did exist. But this is now one example. It's a Dirac fermion. It's the surface state on the surface of a 3D material, and it's very specific. So what about Floquet states in graphene? I think this is an ongoing challenge. We are not there yet, despite like 14 years having passed after the initial proposal by Oka and Aoki. And one of the issues seems to be decoherence and dissipation. This was discussed by Eschliman et al. And Isabella Girt's group, for example, in this paper that I recommend. And hopefully some new results will come out soon where finally Floquet states will also have been seen in graphene, but let's see. Okay, so far so good. Another way of looking at this problem, of course, is not just by photoemission, which is one technique to observe time-resolved states. Another example, another consequence, of course, and prediction by Haldane was that the driven Floquet topological insulator should have a quantum Hall effect. So a Hall effect is a transport measurement, and therefore time-resolved transport was pushed by James McIver et al. In this seminal Nature Physics paper, in order for them to be able to observe actually a light-induced Hall effect. And they were successful. So this is very good. So this is a kind of indirect evidence, if you wish, of Floquet physics at play, but it's not a direct observation. And this was done actually in graphene. So in that sense, there is some evidence that this is possible. But again, the timescales are very short, and it's very difficult to, in fact, discern these Floquet states from other effects that are not directly that cannot be directly seen as Floquet engineering. All right, so this is the summary, the in-between summary. So Floquet theory is an interesting basis to understand dynamics in periodically driven system and to make sense or to kind of come up with interesting predictions for new effects. The Floquet topological insulator, the idea is to induce this non-trivial Haldane mass term by driving with a circularly polarized light. And time-resolved photoemission spectroscopy and ultrafast, in this case, time-resolved femtosecond or sub-picosecond transport are efficient experimental probes for these new light-induced states of matter. So this is good. And now the question, one of the questions that we set out to understand better is, so Floquet is kind of one perspective on a driven state in a quantum material, but there are other ways of looking at driven quantum materials. So this is an experiment, again, time-resolved photoemission experiment from the group of Uli Höfer and Marburg, published in 2019 in Nature, in which they also took the 2D Dirac fermion surface states of a 3D topological insulator, and they drove it with terahertz fields, now at kind of a different frequency from the ones that we've seen before. You remember I mentioned that in Floquet physics, you would like for Floquet physics to be sort of clear-cut and very simple. You would like the driving frequency to be very high, for the field to be very fast. Yeah, this is also important for example, for the Kapitsa pendulum to work. If you shake the suspension point of the pendulum very slowly, then you won't have this inversion of the pendulum. So here they drove this much more slowly, but with very strong fields. And here they see a different effect, namely a population effect, which I haven't discussed yet. They see that if the field has an excursion on one side, you see that there's an excess of
we're experiencing a glitch. I wonder if it's us or if it's Michael. Can someone in the audience?
Yeah, I can hear you. I think it's on his end, Adrian.
Thank you. Well, our messages are now reaching Michael. We're hoping that he'll be back online momentarily. Let's wait for a few minutes. He just replied he's reconnecting in a second.
Hey, sorry, I disconnected.
No worries, no worries. I'm glad we can reach you. I guess do I have to make you co-host again or?
Yes.
Yes. Here we go.
Okay.
Yeah, we lost you here. You were talking
Here.
about the population imbalance.
Yes. Okay, so this is the example with the slow driving in some sense, yeah, shaking back and forth of the electrons within the arc cone. And this is a subcycle effect, yeah. So here we are looking at a time scale that's short compared to the driving frequency. On a subcycle timescale, you can observe this shaking back and forth, and this seems to be in contrast to the shake-off states, which are in some sense time averaged over many cycles. So therefore, now you can ask the question, and we set out to do this. What is the relationship between these two? So how are these two notions connected? A different way of asking the question is how long does it take for a system to realize that it's in fact in a Floquet state, or that it should behave like a Floquet state, right? It's not so clear. You start driving the system, but how many cycles do you need? And this is the story of this recent paper that we just published with these gentlemen here, especially Uli Höfer and Rupert Huber. Ito San is the first author. Michael Schüler was also involved as a theory collaborator, and this was published very recently. And the title is Build-up and Dephasing of Floquet Bloch bands on Subcycle timescale. So it's really the question, pushing Floquet engineering to the limit of very short transient effects, which is important because I mentioned that one of the key obstacles towards observing Floquet states was the coherence and dissipation. So the faster you can look, the better. Also very much in line with the very recent Nobel Prize, which is in attosecond physics, which is even faster than that. So another way of thinking about this problem is the following. So on the one hand, we have intraband currents. This is sort of the slushing back and forth picture. And on the other hand, we can think of transitions, vertical transitions, or interband excitations, right? And in between, we have Floquet Bloch states. And the question is, how are these notions connected, and how and when do Floquet states emerge? So this was done again on bismuth telluride, TI surface state, using mid-IR pumping at 20 to 40 terahertz with megavolts per centimeter field strength, which is sort of about what you can reach. So one optical cycle of this pumping is about 25 to 40 femtoseconds. And the time resolution of the probe, which was 2-photon photo emission probe with 3 EV plus 3 EV photons, the time resolution or the duration of these probe pulses is about 10 to 20 femtoseconds. So this is really subcycle. And the question is, what happens in this regime? And for this, you first have to do curvature filtering and streaking compensation to kind of compensate for the fact that the electrons outside the sample will again see the pump field. And from this, the electric field profile, the temporal profile of the driving field, can be backed out, and it has this shape as that you see below here. So the total duration of the drive is about 200 femtoseconds with a few cycles, not many, but a few. And again, this shaking back and forth that you see here at not too strong excitation can be sort of understood semi-classically, like the shaking of a conical glass of water, if you like. Okay, and then we can sort of semi-classically understand this field by computing the currents with a semi-classical Boltzmann equation, and reconstruct the true electromagnetic field that is seen inside the sample. And this is used then also to compare against theory. So clearly we're now at the boundaries of Floquet engineering. We need some better theory to really understand what's going on there. So in the megavolt per centimeter regime, in fact, megavolts means 0.8 megavolts per centimeter peak field strength at 25 terahertz. The observations are as follows. So you see here the first snapshot. This is sort of when the driving field sets in, and at about -60 time delay, you see that there's already some shaking going on. Yeah, so you see a excess of charge on the right hand side, but you already see that the intensity is not exactly where the original band was used to be. So that's already a bit off. At -50, we already see some kind of disconnect between part of the intensity down here and part of the intensity up here. At -40, it's on the other side. And clearly you kind of start disrupting the actual band. And you kind of see this notion of slushing back and forth again, but with some disruptions to the band structure. And in fact, if you overlay this with the expected Floquet bands, it's kind of, there are some features that are in places where Floquet bands are expected. There's also some intensity where which does not seem to match. So it's very curious what's going on. So what's actually happening here? And clearly we see light wave driven currents and subcycle band engineering. So the theory that accompanied this was done by Michael. The formalism that he used was published, in fact, first in a theory paper. So you have to do a gauge invariant theory of your light matter coupling and compute subcycle time resolved photo emission from the Green's functions, including the matrix element for photo emission, and also the 2pp probe. And the results that are relevant to the experiment are shown down here. So at -100, the population is still almost like in the original band. And then you see this slight excess intensity at the right, and you also see that there's some intensity that kind of wants to almost be in this Floquet sideband, but not quite. Then at -50, you see that there's this more intensity on the left. -40, there's this higher intensity, again disrupted from the original band or separate from the original band. And at -20, it looks like so. So this kind of shows that now if we sort of took a longer pulse, eventually this would resemble more and more the actual Floquet spectrum. But you see that the first features that look like sidebands already appear very early on. And this is kind of the subcycle evolution of the Floquet block states is kind of reproduced. And the upshot from this is that Floquet engineering already starts during like the first and second cycle of the drive. And we liken this to sort of another picture or another way of looking at this is that in the slow driving, you're in the quasi-adiabatic regime. So you have a wave packet that is sort of moved back and forth by the field. In the Floquet regime, you have many cycles. Then we can understand everything in this Floquet picture. And in the subcycle regime, we're kind of in between. Yeah, so we have a wave packet, but it already starts to feel the effect of the periodicity of the drive. So we're really at the limits of time resolution here. And we're challenging both the notion of a semi-classical time evolution of a wave packet within a band and the sort of quasi-static Floquet picture, really exploring the regime in between these two extreme limits. Yeah. And another way of thinking about this is to think about this wave packet as a particle, and the Floquet regime as a wave, which can have interference, and this gives rise to these patterns in the Floquet states. And here we're kind of at the particle and wave nature in between these two extreme limits, if you like. Okay, I think I'll skip this in view of time. So let me just summarize this part of my talk. So they used a mid-IR pump and a very short probe to actually show the emergence of Floquet states on ultra-short subcycle timescales in conjunction with theory this allows us to see on which timescales Floquet effects in fact start to appear. And the hope is that the consequences of Floquet engineering, such as time reversal symmetry breaking, giving rise to a Hall effect, and other interesting effects, many-body Kapitsa pendulum-like of effects that we would like to see and use in materials to change their many-body properties, for example. They can also be manipulated on these very fast timescales, hopefully before dissipation and decoherence set in. Okay, how am I doing in time?
I would say 15 more minutes.
Okay. Yes. Okay, great. So now I've shown you one side of the coin, yeah, one side of this phase diagram. So I've sort of brought you into this regime of strong laser driving, where we have non-thermal effects, we have Floquet engineering setting in, and I promised you to also talk about the other regime, about cavities. So, and at extreme, here we saw the extreme limit of Floquet, the subcycle regime. So what about this quantum fluctuation regime? So clearly, in the strong driving regime, in a laser, we can think of the electromagnetic field as quasi-classical. So we just essentially solve Maxwell's equation and couple them to matter and solve the light-matter coupling problem out of equilibrium without treating the quantum fluctuations of light. In the other regime, in cavities, clearly we have to take the quantum nature of the photon field very seriously, and this can also have interesting consequences. And I would like to motivate this, taking again a step back and think about signatures of electron boson coupling in quantum materials. So you all know certain examples for this, and at the end of the day, photons are bosons, so why should they be much different? For example, electron-phonon coupling, we know. This is monolayer iron selenide on strontium titanate. This has a strongly coupled interfacial phonon mode, coupling to the conduction band of the monolayer iron selenide, and this gives rise to a shake-off state. So this is kind of a replica state shifted down by one phonon energy in this case from the main band, and gives rise to this shadow band down here. And this is kind of reminiscent of the shake-off states that we've seen in Floquet physics. Yeah, these replica states, but here they are the consequence of a classical driving. So here in the Floquet state, they appear both above and below the main band. The reason, of course, is that you can absorb and emit from the bosonic field here, in this case, the electromagnetic field. You can absorb photons from the laser into the material, and you can emit them into the back into the vacuum. Whereas here in the coupled ground state of an electron boson system, you only have a shake-off state below, because it's asymmetric. You cannot do both, right? It's the vacuum state. You couple to the vacuum state, not to a many boson state. That's the difference. But there's some relation between these two limits. So if you now envision taking material and putting it into a cavity, you will again see similar effects, or you expect to see similar effects that you see in a coupled electron phonon system. And in order to study this a bit more systematically, we looked at a particularly simple model that you in fact can solve exactly. And this is the quantum chain in a cavity. So we model a quantum chain. So this is a chain of fermions, or fermionic states between. You can have a hopping parameterized by a T here. Then there's a single mode. We just take a single mode approximation for the cavity. It's a harmonic oscillator at frequency omega naught. And now we again do a minimal coupling, in this case by a pile substitution of the hopping. We dress the hopping by a phase factor e to the I g divided by root L. This is just for scaling. G is the coupling strength between electrons and photons, and A plus A dagger is the quantum analog of the field amplitude of the vector potential A So this is just the if you like position operator, displacement operator of the photonic field. Okay, and this Hamiltonian, interestingly enough, can be recast into the following form. So you can write this as a cosine of the displacement field times t, the kinetic energy of your electrons, plus a sine of the displacement field times the current operator of the electrons j, plus again the harmonic oscillator. And t and j are macroscopic quantities that you can compute if you know the occupations of your bare fermionic band states. And now you can show that, of course, the nk, the occupation at each momentum point, commutes with the Hamiltonian. Therefore, you have a macroscopic number of constants of motion. And you can therefore diagonalize this Hamiltonian very easily. And then the entire problem of solving this coupled problem boils down to just variationally finding the occupation of fermionic states that minimizes the total energy of the coupled problem. That's the idea. Okay, and we did this, and it turns out that the ground state of this coupled system is just the electronic ground state is just the unshifted Fermi sea. I'm not showing this here, but the bosons, the photons in the cavity here, in fact, get turned into a squeezed state where the degree of squeezing depends on the coupling strength between the photons and the fermions in their Fermi sea. So the interesting thing is that the ground state of the electrons is not changed by this. This is a consequence of the fact that there is no momentum transfer between the photons and the electrons in this case, which of course is an approximation, but a good approximation in many cavities. So it's essentially dipole approximation, zero momentum of the photons. So the ground state of the electrons is not changed, but the excitation spectrum is changed. Yeah, this is one of the peculiarities, if you like, of this model. The excitation spectrum is changed, and we do see the emergence of these shakeoff states that I promised. And this is a calculation that you can also do analytically. The results is shown down here. It's in fact an extension of a result that is published in Mahan's book, for example. It's also known as the so-called Frank-Condon ladder. And Poisson distribution is playing a role here. So you see that there's if you plot the spectral function of this coupled problem, you see that there's the main band. It's almost unchanged from the dashed line, which is the bare band of the electrons uncoupled to the cavity. There's a slight renormalization of the band velocity, but it's for a realistic coupling strength, it's not visible in this plot. And then there are shakeoff states with a renormalized cavity frequency. So the cavity frequency does get renormalized by the coupling to the electrons. So you see these shakeoff states at a different energy than the one photon shifted sideband. And this is just because the photons do get renormalized due to the sort of the fact that you have many fermions, but only one bosonic mode, so it feels them very strongly. And then you see that the shakeoff states here at the center in the unoccupied part of the spectrum. So there is a Fermi energy here. I'm plotting the total spectral function, both occupied and unoccupied, but there is a Fermi level in here. So below the Fermi level, the shakeoff state appears below the main band. Above the Fermi level for the unoccupied state, they appear. The sideband appears above the main band. That's the reason why you see this difference here, this seeming disconnect. But this is a correct result. And you also see that there are matrix elements effects. So for example, here at the minimum of the band, there is no intensity, and then it grows as the band velocity grows. And this is again a consequence of the coupling matrix element between light and matter, which is proportional to the band velocity. So where the band velocity is 0, there's no coupling, whereas maximal there is a coupling, and there's a shakeoff state, therefore. Or there's shakeoff intensity, I should say. Okay, so this is the result for the coupled. This is again an exact result for the spectral function of the coupled problem. Again, for non-interacting fermions, this can be solved. Now the one thing that we were interested in is what is the crossover from this quantum shake-off state to the classical, to the Floquet state. And for this, we drove the cavity, or we mimicked the driving of the cavity by preparing the cavity in a coherent state with some average photon number, and the ground state of the electrons, and let them time evolve for a bit of time, and then measured the time resolved spectral function. And the result is shown down here. And we also had to rescale the effective coupling strength in order to recover the free space limit in which the light, of course, does not feel the fermions. Yeah, so that's why this shake-off state below here, as we increase the pump strength, moves closer to the bare frequency or approaches the bare frequency. This is the reason of taking the correct scaling limit. But you also see that, for example, this sideband intensity, which is initially only below the main band and not above, you see that increasing the number of photons in the cavity, the intensity becomes more and more symmetric. And in the Floquet limit at 30 photons here, we already recovered the Floquet limit. And one of the upshots here is that if you can tune your coupling strength, the effective mode volume in your cavity, you don't need millions and millions of photons and a very strong laser in order to reach the regime of Floquet engineering, but you can also already reach it with as few as 30 photons, depending on, of course, the coupling strength of the cavity. But let's say with a modest number of photons compared to the free space limit. And that's, of course, very promising, because I think this would bring into reach the regime of Floquet engineering and all of its other interesting consequences, which we have not studied here, much more readily than what has been possible so far in materials. Let me also mention in the final few minutes some other results that we obtained. For example, now you might ask, well, I'm a correlated person. I don't care about free fermions or TI surface states. You can also do this in correlated quantum systems. Here we looked at a Hubbard model coupled to a cavity, and we looked at the Floquet engineering of the, for example, spin exchange interaction, and or cavity control and Floquet engineering of the spin exchange. And we showed that this can also be done. And in fact, the important result of this paper, I think, is that you don't need coherence in your photon sector to achieve these effects. So you can renormalize your spin exchange interaction in a driven system that is coupled to a cavity, even when the cavity is not in a coherent state. So that's very important. So you can sort of incoherently, in some sense, drive the cavity and still renormalize your spin exchange interaction, and it's tunable. So depending on a certain resonance, for example, between the drive and the Hubbard U in this case, you can increase the spin exchange, you can decrease the spin exchange, and therefore there's hope that you can also change properties of magnetic many-body states, for example, that you might want to study. Another result, which is not related to cavities, I just would like to mention, is that we also computed the effect of screening or the change of screening due to excitation with light from first principles, and showed that the Hubbard interaction in a charge transfer insulator such as nickel oxide can also be renormalized by driving, in this case, by an induced extra screening in the material. Sort of a different effect, but just to also talk a little bit, since I know that some of you are very interested, or more interested maybe, in strongly correlated systems, that there's also interesting things to do with interacting systems and driving. Okay, so I think we should almost wrap up, I guess, Adrian, right? Okay. Then I'll skip ahead a little bit. Okay, let me summarize by showing just one slide of other interesting things, since I think I already summarized enough my results. Let me show you one more slide of open problems. So clearly, instead of a summary, well, I did show you light-induced topological matter, and these are two of the key papers here. One other interesting phenomenon, which I did not talk about, which I think is also very relevant and a largely open problem, is light-induced superconducting back behavior. So using light pulses at specific frequencies to induce an effect that looks like a superconductor, at least from the point of view of time-resolved optical reflectivity. But instead of cooling the material into the superconducting state, you can reach the same state by driving, and in fact also make the state quite long-lived and metastable. This is one other interesting result. We don't really know what is the microscopic mechanism behind this. There are some ideas. And there's hope that we can also use cavities eventually to reach the state and even make it technologically useful, or at least prove that it's really superconductivity, since this is one of the things that's a bit under debate. Here I'm mentioning, if you want to do some further reading, a very nice perspective article by Basov, Everett, and Dave Shea back in 2017. And I, again, shamelessly advertise our review of modern physics. Another thing with cavities that I didn't talk about, but I kind of mentioned the idea of topology and affecting topology with light in the Floquet engineered Haldane model, is that we can also, it was also shown, this is again to not only show some theory ideas. This is an experiment in the group of Jérôme Feist in Zurich, published in Science last year, in which they showed that they can use cavities not to create topology, but to destroy topology, at least, so the other way around. This is not graphene or not Dirac fermions. This is an integer or fractional quantum Hall sample. And they showed that they can affect the location and also the rigidity of these plateaus at different filling factors by placing this quantum Hall sample in a different type of cavity, and thereby change the properties. And finally, again, superconductivity, because it's just so important, I think, and mind-boggling the effect. You can also change superconductivity in the cavity, and this was published, well, part of these results were published in Nano Letters, not the ones on superconductivity, unfortunately. The other ones are in Archive in the group of Thomas Ebbesen in Strasbourg. Again, very difficult to understand the effect, but let me just show you what they did. They put little grains of superconductor onto a gold mirror embedded in the polymer matrix, and they showed by magnetometry measurements that the signatures that look like a Meissner effect are strongly shifted in temperature by some 15 degrees Kelvin, quite a strong effect, from 30 to 45 in this rubidium 3C60 fullerite superconductor, a similar material to the one in which the Cavalieri group showed light-induced superconductivity. They did this with cavities. They also showed that they can deplete TC in a high TC superconductor in YBCO. And I think these are some of the effects that just keep stimulating us in our theoretical research, trying to understand better what's going on in these cavity quantum materials. And I think with this, I'm wrapping up, coming to the end. Just let me again briefly mention our review on cavity materials, and also another very nice paper on strongly correlated electron photon systems, another Nature perspective. So there's plenty of food for thought and further reading. And let me thank you very much for your kind attention, and apologies again for the disconnect earlier. Thanks.
Thank you, Michael, for a super nice and interesting talk. Now we open the session for questions. If anyone in the audience has a question, please feel free to unmute yourself. I see a hand. Alex, do you want to unmute yourself? Oh, you're uploading. Sorry. Anyone in the audience wants to ask a question? I see a raised hand.
Hi, thanks for the nice talk. I had a quick question on the sort of first part of the talk on the Floquet system. I was just curious if, apart from the photo emission results, as a sort of, are there any other probes like low energy optical conductivity or something like that that could also sort of show signatures of this this sort of a effect?
Yes. Oh, yes, absolutely. In principle, yes. In principle, you could also look at this from the point of view of optics. I did mention that there's transport, right? Timers of transport. I'm not sure about, I mean, the problem is, I think okay, let me put it like this. Why is photo emission so nice? It's so nice because we directly look at the single particle states, or the single particle excitations, I should say. And there we understand best what are the consequences of Floquet dressing. In the low energy optical conductivity, in principle, you could also see Floquet dressing like effects. So you could see changes in your optical spectrum. The problem is, how do you interpret those changes in your optical spectrum? Because it's much more sensitive in a sense to the grounds, or to the state from which you're starting to. So if you think of this in the sense of linear response theory, right? You compute an excitation spectrum, an optical excitation spectrum. You'll be sensitive not only to where the states are in energy, but also how they're occupied. And all of this will kind of conspire to give you the optical conductivity that you're measuring or computing in that case, right? So here, for example, if I look at the center plot here, right? So all of a sudden you've occupied all of these other states, and you have all this extra intensity in your single particle levels. And now you have to compute all of the initial and final state combinations that are possible. And it quickly becomes just much more complicated. So I think it's much harder to disentangle different effects in an optical spectrum. The reason why it works so nicely in transport is because it's very selective. They look specifically in the Hall effect channel. They look specifically in the transverse conductivity. For example, the longitudinal conductivity is also less. It's also less obvious what are the effects, what are Floquet effects versus other effects that are going on in the driven system. I think that's the main reason why we haven't seen so many examples yet.
Thank you.
I'm sure so just to mention this, I'm sure people have seen Floquet physics, but maybe they couldn't clearly pinpoint what are the Floquet effects.
There's the paper by Dave in nickel phosphorus sulfide, where they see a suppression of second harmonic generation only during when the pump is there, and there's a claim that that's to in the optics, in an optical.
Yes. But this probably goes in the same direction, right, Alberto? That it's in some sense, this SHG signal is all in some sense more selective.
It's also it's what you say, right? Like it involves knowing if a state is an available transition or not. So it could be that your population of that excited state, or like the cross. Yeah, so I agree. Photo emission, it's a very much direct probe. So
yeah, but it has other problems. I mean, clearly competition with laser-assisted photo emission is one issue. You also have to apply this streaking compensation, which is not so straightforward. So there are a number of issues that have to be addressed, and it's a terribly complicated experiment. So in that sense, I'm happy that I'm a theorist. I only have to help them understand this. I don't have to actually do the data analysis and the measurements. It's very difficult. Right.
All right. Any other questions from the audience? I have a few questions, but I think I'm gonna ask you privately because
there's a question.
Oh, there's a question here from in the chat. In the 1D cavity example, since there is no dissipation, what is the final state at very long time?
Oh, yes. That's true. You mean here, right?
The effects or some dressing.
Yes. Oh, of course. Yeah. So at very long time, actually, we didn't even look at this long time dynamics because, as you mentioned, without dissipation, it doesn't make much sense. I think you will just heat up the thing. I don't think that you get a condensed state. Or what do you mean by condensed state? You mean a Bose-Einstein condensate of the cavity mode or something like that?
Yes.
Okay. Well, we didn't even look into this, so I can't give you a very good answer. I would think that this is probably beyond the model. To really think about BEC, for example, for a true BEC, you actually need, well, I guess strictly you don't need interaction between the bosons, but it's only a single mode, so I don't really know how to think about a Bose-Einstein condensate of a single mode model. This is probably too simple. Really, the whole point of studying this model was not the long time dynamics, but really just to look at the emergence of Floquet physics from quantum fluctuation effects or light dressing effects with the quantum fluctuations. Yeah, we're actually trying to figure out more interesting, more realistic things right now. For example, we're trying to couple fermions to a whole branch of bosonic modes as you would have them, for example, on a plasmonic surface. Then you can actually start asking these questions. Does that make sense?
Yeah, they say thanks.
Okay. Good.
All right. If there are no other questions from the audience, let's thank Michael one more time.
Thanks a lot.
And I'll be in touch.
Yes, let's be in touch.
Hey, Michael.
And also, Alberto, we'll talk.
Yeah, I'll send you a
separately.
WhatsApp and we'll figure it out.
Okay, great.